This next topic for our differential equations unit is going to involve some differential equations in which the change in one variable, in this case y, with respect to time, dt, is going to be proportional to the amount of that specific variable, that amount of y that we have. Right? So the rate of change of some quantity is going to be proportional. In other words, it's going to be a constant times that variable. Okay? So k is going to be a constant. And so what we're going to do is we're going to use our techniques for solving a separable differential equation to solve this separable differential equation. We'll end up with dy over y equals k, our constant, times dt. And we'll just integrate both sides. So on the left, we're going to get natural log absolute value of y. And on the right, the integral of a constant with regards to the variable t should be that constant times t. And then we also have to add a plus c to it. So we've got two different constants in here, actually. We've got c and we've got k. And what we're going to do now is the same thing we normally do at this point, is we're going to plug in our initial condition. But if we look at this, we don't really have an initial condition. But we do know that the way we can notate the amount of y that we have when t is 0 would be y naught, right? That's our initial amount of y naught. So we do know that when t is 0, y should be represented by y naught. So the natural log of the absolute value of y naught is equal to, if t is 0, that's just c. And the way we're going to be thinking about this is we're going to be thinking about this in terms of real actual quantities of things, where the value of y, or the value of y naught, is always going to be some positive number. And if y naught and y are both some positive number, those absolute value signs after the natural logs are going to become insignificant. So we're really going to say our c value is going to be natural log of y naught. And so if we plug that back in, we're going to end up with natural log y. And again, I'm ignoring the absolute value because we just said y is always going to be a positive value. And we'll have k times t plus natural log y naught. And from there, we'll just exponentiate to solve for y. So if we raise both of those to a power of e, we get y equals e to the kt plus natural log y naught, which is the same as e to the natural log of y naught, just like we did in the last lesson. And e to the natural log of y naught is just y naught, and we're left with y equals y naught e to the kt. And this is a formula that you should be familiar with from previous math classes. This is the exponential growth and decay formula. So effectively what we're looking at when we see this differential equation, that dy dt is equal to ky, that's telling us that we have exponential growth or decay. And that this number k, this constant that's in front of the y, is going to be directly correlated to the k in our exponential growth formula. So just a couple things we want to remember about this, and we should all have used this formula before in a pre-cal or a intermediate algebra, integrated math 3 course. But that k is always going to be a positive value. Now, sometimes what we'll do is if we want decay, we will just throw a negative sign in front of that k value. But the value of k itself is still going to be a positive number. So this will be our formula for decay, with the y equals y naught e to the negative kt, and the y equals y naught e to the positive kt will be our formula for exponential growth. So what we're going to do is we're going to just kind of work our way through a couple of problems sort of surrounding this. None of it should be too different from anything you've done in previous math class. The first thing we're going to do is we're going to see if we can come up with a basic formula that tells us what the half-life of any radioactive element is, given the fact that we know the K value. Or it'll allow us to find the half-life if we do know the K value. So what I've done here is I've set up the normal y naught e to the negative kt for decay on the left-hand side, and I said my final amount is now going to equal half of what I started with, because that's what half-life means. It means that half of those radioactive nuclei have decayed. So in order to solve this for t to find the half-life, all we've got to do is cancel out the y naughts to get e to the negative kt is equal to 1/2, and then take the natural log of both sides. And I really don't like writing natural log of 1/2. Normally, we'll rewrite that as natural log 1 minus natural log 2, and the natural log of 1 is 0, so that's just negative ln2. So we end up with negative kt equals negative ln2, or our half-life is equal to natural log of 2 over that constant k. And this will be a good little formula that'll be helpful for you to remember, especially if you are given a differential equation, dy dt equals some k times y. You'll immediately know the half-life because you can look at the differential equation, see what the k value is, and then just do natural log of 2 divided by that to find the half-life, which is exactly what we're going to do here. We've got samarium 151 that's modeled with this differential equation where t is measured in years. And we just want to know the half-life. Well, the value of k here in our differential equation that we can see yields exponential growth because it's dy dt equals k times y is 0.0077. It's not negative, right? Because the value of k is always going to be positive. So our half-life is going to be the natural log of 2 divided by 0.0077. And of course, for a lot of these, we're going to want to be able to get a decimal approximation. So we'll go into our calculator here. We'll do natural log of 2, and we'll divide it by 0.0077. And we'll end up with 90.01911,436. And so we'll just say that that's approximately equal to, and we'll say 90.019, we'll write the whole thing out, 11436. But it's also perfectly acceptable on both my test and the AP tests to round this to 3 decimals. You should never, though, round to less than 3 decimals unless the problem specifies otherwise. So here we're given a half-life for carbon-14. We know the half-life is 5,700 years. And we want to find the age of a sample in which 10% of the radioactive nuclei that were originally present have decayed. So the first thing we're going to recognize is that we know we're going to need to use y equals y naught e to the negative kt, which means we need a value for k. Well, since we know that half-life is equal to natural log of 2 over k, we can very quickly solve that for k to get k as natural log of 2 over 5,700. And if this was my test or the AP test, you wouldn't want to round that value until your final answer. So we're just going to leave our k as ln2 over 57. And as we said a minute ago, we know we're going to use y equals y naught e to the negative kt. But we need to figure out what our starting amount and our final amount is. Well, our starting amount can just stay as y naught, but our final amount has to indicate that 10% has decayed. Well, if 10% has decayed, that means that we have 90% left. So if we have 90% of what we started left, that would be 0.9 of y naught, which should be equal to y naught e to the negative k, or natural log 2 over 5,700 times t. And now we just have to go on and solve for t to find how old that sample is. We can divide both sides by y naught, and then take a natural log. The natural log of 0.9 should be equal to the natural log of e to negative ln 2 over 5700 times t, and ln of e cancels out, so we're just left with negative ln 2 over 5700 times the time. And just a quick little bit of rearranging ought to give us an exact value of 5700 times the natural log of 0.9 divided by the negative natural log of 2. And we will go ahead and get ourselves a decimal approximation for that. So for that, we'll just use our graphing calculator here. And we are looking at the 5700 times the natural log of 0.9. And then we want to divide that by negative natural log 2. And that ought to give us 866.4176326. And we'll just round that to 3 decimals. So it was 4176. So that will be 866.418 years. That's the age of that sample. And of course, we can apply this into an exponential growth formula as well. So here we're going to have a population of wasps, and they're going to grow at a rate that's proportional to the population. So that tells us right off the bat that this is exponential growth. And we know that the initial population of the colony is 10, and it grows to 50 after 30 days. So we're going to start with that goes from 10 to 50 in 30 days. That's going to allow us to find the value of k. So we'll set up our formula that our final amount is 50, and our initial amount is 10, and we have e to the positive k this time, and no negative in front of it because we're growing, and then 30 days, so I'll put a 30 up there. That's the k. And we'll just solve this for k. Divide both sides by 10 gives you 5 equals e to the 30k, and taking a natural log gives you natural log of 5 equals 30k, telling us that the value of k in this problem is natural log of 5 over 30. So now that we have the value of k, we should be able to go in and determine how many days after May 1st the population reaches 100 wasps. And so since we're talking about how many days after May 1st, we'll start with our initial population of 10 that we had on May 1st. And since we now know the value of k, we'll put that in. 10e to the natural log 5 over 30 times t. And our final number of wasps that we're looking for should be 100. So we'll put 100 on the other side. Now we're just solving for t. So we'll divide both sides by 10. And then we'll take a natural log of both sides. And then we'll rearrange, multiply by 30, and divide by natural log 5. And since we probably don't have a great idea of what 30 times the natural log of 10 divided by the natural log of 5 is, we'll go back in and we'll put that into our calculator. 30 natural log 10. And then we will divide that by the natural log of 5. And that'll give us 42.92029674 days. And we'll round to 3 decimals. And when we do that, it was 9202 as our decimals, which means it should round to 920. Make sure you include that 0 in your rounding. Don't just write 42.92 because the readers on the AP test will assume that you rounded to 2 decimals instead of 3 if you don't throw that extra 0 on there. So now we're going to look at a couple of other quick applications of this exponential growth. One is compound interest, which you should hopefully have talked about compounding interest, whether you're compounding it annually, quarterly, monthly, daily, or even if you were compounding it continuously. And so we're going to kind of take a look at the regular old formula, right, for compound interest, where you're compounding in times per year. A equals your final amount, where P is your principal. So we have A equals P times 1 plus the interest rate, R, as a decimal, divided by the number of times compounded, all raised to the power of the number of times compounded per year times the number of years, T. And so you should be familiar with the formula that you get for continuously compounding interest from your previous class. But if we think about what does continuously compounding the interest mean mathematically, it means that this value n needs to go towards infinity. We have to be compounding at every instant in time forever, for the entire year. And so the way we make n get exceptionally large in math and calculus is we let n go towards infinity by taking a limit. So we're going to see what happens if we take the limit as n approaches infinity of p times 1 plus r over n to the power of nt. And so the first thing we'll do is just plug in infinity. If we do that, we have p times 1 plus r, a constant, over infinity. Well, r over infinity is 0, so 1 plus 0 is 1. And then in the exponent, we have infinity times a constant, so we have p times 1 to the infinity. And now we haven't yet talked in this class about 1 to the infinity, but 1 to the infinity is another indeterminate form. We can't evaluate 1 to the infinity. And so what we're going to do is we're going to use a technique that's usually taught in Calc BC to evaluate this limit. So we're not going to do the full proof of it here. But if you happen to be taking the BC test, it's good to know this way to solve limits of the form 1 to the infinity. It also works for limits of another indeterminate form that we haven't talked about, which is 0 to the 0. So what we're going to do is, first off, we're going to just take that p that's a constant and pull it out so I don't have to deal with it. And we can take a constant out of a limit anytime we want. But then what I'm going to do is, in order to get rid of that infinity that's in the exponent, I'm going to take a natural log of 1 plus r over n to the nt. But I can't just take the natural log of something within a limit without directly affecting the value of the limit. So what we're going to do is we're actually going to do e to the natural log of 1 plus r over n to the nt. So if I introduce e to the natural log of something, that doesn't affect the value at all. And so now what we've done here is we've rewritten this in a form that's going to allow us to take this nt and pull it out in front of the natural log, and it doesn't actually affect what our limit is. So we end up with p times a limit as n approaches infinity of e to the nt natural log 1 plus r over n. And one thing that you could normally do, that we're not going to do the proof for, is we could actually change this so that this was e to the power of the limit as n approaches infinity of this nt natural log 1 plus r over n. But I'm just going to leave it like this, and anything that we could normally regularly do with a limit, like using L'Hopital's rule, for example, as long as this piece up here is of a form that we could use L'Hopital's rule, we're still going to be allowed to use L'Hopital's rule for the fraction within the exponent of the e. So if we now plug in infinity, though, we can see that this is just an infinity times natural log of 1, and natural log of 1 is 0. And infinity times 0 is an indeterminate form that we have talked about in this class. And one of the ways we can get around that is just by, instead of multiplying by n times t, we can divide by 1 over n times t. So we'll have a limit as n approaches infinity of e. Now we have a pretty big power up here. It's going to be natural log of 1 plus r over n over 1 over in t. And now the thing inside the exponent, well, both the numerator is equal to 0 because it's natural log of 1, and the denominator is now 1 over infinity, which is also 0. And so now the piece that's in the exponent is eligible for us to use L'Hopital's rule on it, right? We end up with e to the 0 over 0. So we'll just use L'Hopital's rule as we normally would, taking the derivative of natural log 1 plus r over n and the derivative of 1 over n t. So we've got the limit as n approaches infinity of e to the power of, and then the derivative of natural log of 1 plus r over n, that's natural log of u, so it's 1 over 1 plus r over n. And then the derivative of 1 is 0, and the derivative of r over n, well, if r is a constant, that looks like, up here in the corner, r into the negative 1, which would be negative r into the negative 2, or negative r over n squared. And then down here in the denominator, 1 over t is just a constant. And then we have the derivative of 1 over n, which is the derivative of n to the negative 1. The derivative of n to the negative 1 is, what we just did a minute ago, negative 1 over n squared. And now we should be able to do a little bit of simplification here. So both the negative in front of the r over n squared and the negative in front of the 1 over n squared should cancel. And if I'm dividing both the numerator and the denominator of a complex fraction, but the same thing, both of them are being divided by n squared, I should be able to cancel out those n squareds. So this 1 over t right down here that's in the denominator that I'm dividing by should flip up and be a t in the numerator up there. So I'll effectively end up with something that looks like this. The limit as n approaches infinity of e to the power of rt, right? Because we had the r that was already up here, and we had this 1 over t, which goes up into the numerator as a t. And then that'll be over 1 plus r over n. And looks like I've forgotten it a couple times out here, the p out in front of the limit. We'll make sure we have those in there. And now 1 plus r over n in that denominator is, as n goes towards infinity, r over infinity is 0, and 1 plus 0 is 1. And so this just becomes e times e to the power of rt, which should be a formula that you are quite familiar with back from pre-calculus or the math class that you took before that, integrated math 3 most likely. And that's the PERT formula that I was talking about for continuously compounding integers. And this is where it comes from. It's just the limit as n approaches infinity of the regular compound interest formula. So we have a equals e to the rt. And so just to make sure we can use both these formulas, we're going to take one quick situation with this and see if we can find how much money we have given both of these accounts. So for the first one, our final amount will be equal to our principal, 800. And then the first one, we are compounding quarterly. So this is p times 1 plus our interest rate of 6.3%, written as a decimal, over our number of times compounded. Quarterly would be 4 times per year. And then to the power of n, 4 again, t, which is 8. And so we'll just need to use our graphing calculator, or any calculator for that matter, to figure out what that value is. So let's go ahead real quickly and do that. We're looking at 800 times 1 plus, and if your calculator will give you this little fraction here, you might as well use it. If it doesn't, just make sure you put your fraction in parentheses. 0.063 over 4. Then close your parentheses to the power. We had 4 times 8, so that'd be 32. And it looks like we end up with $1,319.07. And we'll round to the nearest cent here. $1,319.07. And then if we want to do this continuously, it should be A equals P E to the R 0.063 T, which was 8 years. And so we'll just use that formula. We'll throw that into our graphing calculator. So we've got 800 E to the power of 0.063 times 8. And it looks like that gives us $1,324.26. So a little bit more than the other way around. Quarterly comp. So we have one last application of this exponential growth, and it's called Newton's law of cooling. Newton's law of cooling. And so you can see it looks very similar to what we've been doing, where we have a final of something equals the initial e to the kt or negative kt in this case. But what we've added in here is we've added in two different variables here, t minus t sub s and t naught minus t sub s. And so what we're doing with Newton's law of cooling is something like where we will take some object that we know its initial temperature, and we'll put it in a freezer that we know the temperature of. That'll be our T sub S, the temperature of the surrounding medium. And then we'll look for its final temperature after a certain amount of time. Or perhaps we may heat something up. This also works for heating something up, where we might throw something into an oven to cook it or something like that, or to heat up a plate. And we want to know how long it takes to get to a certain temperature. And so if we were to use Newton's law of cooling to cool something, we'll throw a negative up there, the negative kT. But if we were to use Newton's law of cooling to heat something, it will just become e to the kt. So let's see if we can do one quick and easy problem here. We've got a hard-boiled egg that has an initial temperature of 98 degrees Celsius. We're going to put it in a pan under running water, so that temperature of the water is always 18 degrees Celsius. And we know that after 5 minutes, the temperature of the egg is 38 degrees Celsius. We want to know how much longer it takes to get down to 20. So we're going to have to find the value of K, and we'll do that by using the initial temperature of 98 and the final temperature of 38 after 5 minutes. So our final 38 minus the surrounding temperature, 18, ought to equal our initial temperature, 98, minus our surrounding temperature of 18, times e to the negative k t, where t is 5 minutes. So 38 minus 18 is 20, and 98 minus 18 is 80. And when I do the 20 over here on the left divided by the 80 here, 20 over 80 is going to be 1/4. We've got 1/4 equals e to the negative 5k. And when we take the natural log, we can do the same thing as before. Natural log of 1/4 is natural log of 1 minus natural log of 4. Or effectively, it's just negative natural log 4. So the value of k here for us is natural log of 4 divided by 5 when we cancel out those negative signs. And so the question then asks, how much longer is it going to take the egg to reach 20 degrees Celsius? Well, when we did the problem about the wasp, we wanted to know the total time, but now we just want to know how much longer. So this time, we'll start with our initial temperature being the 38 that it's already reached. If you started with the 98 again, you'd have to just subtract 5 from here. We might as well just start at 38 this time. So our final temperature now is going to be 20 minus the 18 that it's in the surrounding. And now our initial is 38 minus the 18. e to the negative k, so natural log 4/5 times t. And all that's left is to solve for t. We end up with 2 and 20. And when we divide the 2 by the 20, we get 1/10 equals e to the negative ln 4/5 times t. And once again, natural log of 1/10 is natural log of 1 minus natural log of 10, or just the negative natural log of 10, which is now equal to negative natural log of 4/5 times t. For t is when we cancel out the negatives and multiply by 5 and divide by the natural log of 4, we get t equals 5 ln 10 over ln 4. And we can use our graphing calculator to see what that comes out to approximately be. So 5 natural log of 10. And we're going to divide that by the natural log of 4. And it looks like we get 8.304820237, which will round to 8.305. And it looks like our units were minutes here, so we'll make sure to include units. And that is our final answer. And that's the last little thing we're going to do with exponential growth and decay. And this is actually the second to last little lecture of our unit. We've just got one more to go on what we call rate or accumulation problems. It's going to be really quick and easy, and then we'll be done with our unit on differential equations. That's it for today.